In this video, we are going to discuss about AdHoc testable design technique. So, in this technique, is to increase the testability by making nodes more accessible at same cost by inserting a physically more accessible circuit to the original design. That is, we are going to break the large circuit into a sub-circuit. So, some of the following techniques are, first one is partition and mux technique. So, as we know that since the large circuits and functional blocks are difficult to test, such circuits are partitioned and mux is inserted so that some of the primary inputs can be fed into the partitioned parts through the help of the mux. So, this AdHoc technique has a drawback of it can be used for the smaller circuit only. So, with the help of this mux, we know that it is controlled by the control signals. Okay, by using this technique, number of test patterns can be reduced, and but the number of accessible nodes get increased. Okay, so that is what our ultimate aid. First, we consider the 32-bit counter, which can be reduced. So, for the 32-bit counter, we have 2 power 31 test patterns are required, right? So, if that circuit is reduced into 2 parts, then the number of test pattern to check the circuit get reduced to 2 power 15, right? So, this can be done by dividing the whole circuit into 2 parts like that. So, this is one example. So, here the total circuit get reduced into 3 parts, and I have inserted 2:1 mux with the help of a control signal. So, the number of accessible nodes get increased, and number of test pattern get reduced. Right. So, but this technique will add a circuit delay, and it will increase the chip area. Next, initializing the sequential circuit. So, we know that if we have a 3-bit counter, we don't know the value of QA, QB and QC, right? That is the output of the flip-flop at initial value. It can start with 0, 0, or it can be any of the random values, right? So, the state of a sequential circuit can be brought to known state through the help of initialization. So, this can be done by connecting a asynchronous reset or preset signal from primary or controllable input to the flip-flops or latches. So, if we don't know the initial state of the sequential circuits, it is very difficult to test, right? So, with the help of the initialization technique, we can know the state of the circuit, right? Next one is disabling the internal oscillators and clocks. So, to avoid the synchronization problems during the techniques, we need to disable the clocks and internal oscillators. This can be done by ORing the internal oscillators and clock with the disable signals. Then it is followed by the testing signal. So, let us discuss the block diagram for this one. So, here the internal oscillator is not with the disable signal. So, if the disable signal is 1, you won't get the internal oscillator signal. After that, the test signal is not with the disable signal. So, therefore, the test signal will be provided to the circuit. Okay, and thereby the internal oscillator or the clock get disabled completely. Next one is avoiding the asynchronous logic and redundant logic. So if we if we know that the designing and the testing of the asynchronous logic is a bit more difficult when compared to the synchronous logic, because asynchronous logic is faster, and it is difficult to design, and the state transition are difficult to predict. Okay. So, and also the operation of the asynchronous logic is sensitive to the input test pattern, and it will often creating a race problem and hazards. So we know that in order to avoid the static hazard, we will add some redundant circuit to the logic, and that will increases the reliability of the circuit. But this redundant nodes, that the circuit, cannot be observed, since the primary output value cannot be made dependent on the value of the redundant node. Hence, the certain faults cannot be tested or detected. Okay, suppose if f is equal to ab plus a bar c. So this is my logic, and I'm going to give one, and the one, the b value, so it is suddenly, if it's changing from 1 to 0, you can see there is a 101 at the output. So this will causes a momentary, instead of the whole one, instead of getting 1, I'm getting 101. So this is nothing but the static hazard, right? So this can be avoided by adding a redundant circuit, right? So if I add the redundant circuit, this value, the BC, the output of the BC value is always 1. So if I add these three value with the OR gate, I will get the output as 1. Okay. So thereby this static hazard get eliminated. But if you see, if I'm so this is a circuit. If I'm if suppose the output of the redundant logic is stuck at 1. Okay, so if I am giving 0 0 at the input of ABC, okay, I will get, instead of getting the 0, I am getting the output as 1. Okay, so therefore this fault is undetectable, uh, and this associated gate, that is the redundant gate, must be removed without changing the logic function. So the use of such a redundant circuit make the circuits more complex and difficult for the test generation. In order to increase the reliability and increase the yield, the redundant circuit must be eliminated. So next one is avoiding the delay dependent logic. So consider the pulse generation circuit. So here the pulse get generated, because here you will get the output like this. So it is so here you can see it get delayed, right? It get delayed, and so if I and to this one, you will get the output like this, and it will produce as a pulse generation, and without this pulses, nothing but the delay of this three inverters. So, okay, so if you say most of this automatic test pattern generation programmers avoid these type of circuits in order to minimize the complexity of the program, uh, and considering the circuit as a redundant logic for the combination circuit, as they uses a delay dependent logic. Okay, so this must be avoided.